Alright, hello everyone. Welcome back to this series where I take you through each chapter of the H2 physics syllabus and try and make sure that you understand all the learning points that are present within each chapter. Okay, so today we are talking about forces and moments. Let's jump straight into the types of forces that are present. So firstly, we've got this idea of friction force. Correct? Everyone knows what's friction force. Friction force is the force that opposes motion, right? Opposes motion or the tendency for relative motion. Okay? What this means is that, for example, if you have two bodies, right, trying to slide across each other, correct? This one is going here, this one is going here, and there is this area over here where they are overlapped and they are sliding over each other. Okay, so this is where there will be friction, right? Straightforward. All right, let's look at another type of force. So the next one, we have normal contact force. So what is normal contact force? Normal contact force is force that is exerted on a body, okay? Exerted on a body when it in contact with a surface. All right, note that it is normal. What does normal in physics mean? It just means that it is perpendicular. Okay, so let's draw a diagram for this force as well. Okay, so let's say we have this particular slope, right? And we've got a box on this slope. And this box is in contact with the slope itself, right? In this case, where will my normal contact force be pointing? It will be pointing towards here, right? It will be perpendicular to the surface, right? Perpendicular to the surface. And then if it's flat on the ground, right? This box, where will be my normal contact force? It will be from the surface to the top, right? Always remember that my normal contact force must originate from the base where there is contact, right? Don't draw the normal contact force starting from here, for example. Okay? All right. Let's carry on. So let's look at another type of force. So we've got tension force. Okay, what is tension force? Tension force is the force that is exerted by what? What can exert tension? It's usually a string or a rope that is pulled taut. Okay, so this idea of it being pulled taut is very important, right? If your string is sagging like that and you are not really pulling on this, is there tension? No, right? It needs to be put straight, correct? Then, okay, so example, if I'm holding on to this end or I'm holding on to this end, right? Then now we have tension. We have tension within the string, okay? So next up, we have buoyant force, okay? Buoyant force. What is buoyant force? Buoyant force is also known as upthrust. So buoyant force is the vertical upward force, right? That is exerted on a body submerged partially or fully in a fluid. Okay, so keyword here is that it must be submerged partially or fully in a fluid. Okay, so how does this force arise? Let's think about it. Let's say we have this beaker of water, right? And I put in a cylinder, okay? What happens is that my cylinder experiences a force upwards along this surface, okay? Due to the pressure of the water over here, right? However, this surface in the deeper side of the fluid exerts greater pressure and hence force as compared to the top side. Okay, so you can imagine the bottom side exerting more pressure than the top. As such, there's a pressure difference, right? And there is a force difference and a net upward force acting on this object. Okay, so if this upward force is greater than this body's weight, correct? What will happen to my object? My object will float. Otherwise, if the weight is in fact larger than the upthrust, then the object would sink. Okay, so that's the idea of buoyant force, also known as upthrust. Okay, next, let's look at drag force. What is drag force? Drag force is the force that resists a body moving, okay, a body moving relative to a fluid. Okay, so this drag force depends on multiple factors. Okay, for one, we have the shape of the object, okay, as well as the viscosity of the fluid. Okay, you can imagine if the object is more aerodynamic, right? For example, it has a shape of this, right, going through the water, as compared to this going through the water, right? You expect this one to have less drag force acting on it by the water as compared to this body, right? Additionally, for viscosity, so let's say we have an object traveling through water as compared to a thick gluey substance. You expect that the thick gluey substance results in significantly more drag force on the object as compared to the plain water, right? So that's the idea of drag force. And a very classic example of drag force would be that of air resistance. Okay, so moving on, we have spring force. So springs can be stretched or compressed to provide a force that is given by this thing called the Hooke's law. Okay, so what is the Hooke's law? It is given by F, the force, is equals to K, some constant, multiplied by X, the extension. Okay, so this is the force, let's say spring force, the constant, as well as the extension slash compression. Okay, so the spring force is given by the Hooke's law, right? Okay, there's a very important criteria for Hooke's law to apply, and that is the proportionality limit of the spring is not exceeded. So let's take a look at what that means. So let's say if we try and plot out this graph of F against X, the spring force against the extension. If proportionality is not exceeded, this is how the graph will look like, right? It will be a linear graph because K is a constant, right? However, if we stretch the spring too much, what will happen is that we will have this kind of deformation, okay? So this is what we refer to as the limit of proportionality, okay? And once this limit is exceeded, the spring will no longer return to its original length once the force is removed, okay? So Hooke's law applies only within my limit of proportionality. So within here to here. Okay. Alright, so now that we have taken a look at all of these forces, right, the commonality between them is that they are what we call contact forces, right? It's between two bodies that are in contact, okay? So apart from this, we also have what we call non-contact forces, all right? So let me write down here, non-contact forces. Okay, so these forces are able to act without being in direct contact. And this also brings us to this idea of a field of force. What's a field of force? A field of force is a region of space in which bodies experience a force associated with the field. So the last line might be confusing for you. What does it mean by associated with a field? What this actually means is that this force can only be experienced by bodies with specific properties with respect to the field. Okay, so let's give some example. Firstly, we have gravitational field. Right? Okay, I believe we are all familiar with this. So what's a gravitational field? It's a region of space where gravitational force acts on a mass, right? So in this case, mass is the property that the field interacts with. All right, so let's look at another example. Let's say we have an electric field. Correct? Can you guess what the electric field acts on? It acts on charges, right? So electric force acts on electric charges. Okay? And then lastly, we have magnetic field. Magnetic field is a field where magnetic force acts on current carrying conductor moving charge or a permanent magnet. So for all of these properties, they are specific to the field. Okay, so only objects with these properties can experience a force in these respective fields. We'll learn about these specific fields in our subsequent chapters. Alright, now let's take a closer look at gravitational field. Okay, so gravitational field provides a special force that we call weight. Right? So what is weight? Weight is the force experienced by a body of mass in a gravitational field. Okay, usually what we refer to is for bodies near the surface of Earth. Okay, and usually what is this given by? You should have learned this in secondary school, right? W is equals to mg, right? Weight is equal to mass times our gravitational field strength. Okay, it is also the gravitational acceleration. So for our model of weight, we can see it as a force, right, that acts vertically downwards towards the center of the Earth through a single point on or outside the body. Okay, so for example, given this box, right, we can say that this weight acts vertically downwards towards the center of the Earth through this singular point. Okay, and what do we call this point? Call it the center of gravity. Okay, and for a more exact definition of center of gravity, it is the point at which the entire weight appears to act. Okay, so the weight appears to act entirely on just this one point. Okay, and let's give another example. Let's say we go back to our slope example. Right, the CG will be here and it will still be pointing downwards vertically. Okay, and this is the weight. Okay, now that we have talked a lot about forces, right, let's take a look at our moments. Okay, let's expand upwards. So what is moment? The moment of a force at a point is the product of the force and the perpendicular distance of the line of action to the point. Okay, so let's try and expand on what this definition actually means. Okay, so for example, we've got this stick over here. Let's say that we apply a force as such to this end of the stick. Okay, so some force F, right? This force can generate a moment about this end of the stick. Okay, and the moment, okay, moment is represented by tau, is equal to this F, right, multiplied by this distance over here. Okay, and this distance, note that it must be the perpendicular distance from the force's line of action. Okay, so for you to better understand what it means by the perpendicular distance from the line of action, right? Let's say we have another stick here, right? And then we still have a force that acts downward as such. Okay, how do we find the moment about this particular point, right? We can extend our force's line of action such that we can find the perpendicular distance from the point to our force's line of action. Okay, so in this particular case, let's say that this stick is angled away from the horizontal by theta, right? Then we can basically resolve this distance into the vertical and the horizontal component, right? And this pink component that is actually perpendicular to the line of action is given by d cosine theta, right? Okay, so tau in this case, the moment is equal to f d cosine theta. Okay, all right, let's give one more example. Let's say similarly, we have a tilted stick, okay, with this force F acting on it. And we are trying to find its moment about this point. Okay, so since this is given by theta, right, we can also resolve our force with respect to these two directions. Okay, and in this case, we will get moment is equal to F cosine theta, because this component, right, is F cosine theta times our D, right? So we'll use our original length of D. Okay, so that's our two ways of finding moment about a point for a force. Okay, so the other important concept for moments is this idea of a couple. What is a couple? A couple is a pair of forces that are equal in magnitude but opposite in direction. Okay, and important caveat, lines of action do not coincide. Okay, so this is what a couple is. The special thing about couples is that they only produce rotation but no translation. Okay, so for example, if I have something like that, right, and let's say this is force F, this is force F as well, right, of magnitude F, I can take moment about any point on this, right? I can take moment here, I can take moment here, I can take moment here, right? I would see that the total torque given is moment equal to total distance times force, okay? Where basically we are referring to this as our total distance, okay? So this is a special relationship that couples have. Okay, now that we have talked a lot about both forces and moments, right? Let's take a look at this idea of equilibrium. Okay, for a body to be in equilibrium, it needs to satisfy two criteria. Okay, one is that it needs to be in translational equilibrium. Okay, and the other is that it needs to be in rotational equilibrium. So these are the two conditions that it needs to satisfy for the body to be in equilibrium. Okay, and then we also have a third optional property, is that if the body is at rest. Okay, if it's at rest, then we call it static equilibrium. Okay, So now let's talk about translational equilibrium and rotational equilibrium. All right. So what is translational equilibrium? It is when there is no net force acting on it. Okay, acting on the body. Okay. And then for rotational equilibrium, we have no net moment about any point on the body. Okay, this idea that it's on any point is very important. Okay, so what does it mean by there is no net moment, right? This brings us to this idea of principle of moments. Okay, and this basically states that if the body is in rotational equilibrium, right, the sum of clockwise moments at any point must be equals to the sum of anti-clockwise moments at the same point. Okay, so that's the idea of principle of moments. So overall, these are basically all the concepts that are within this chapter of forces and moments. Okay, so that's it for this chapter. If you'd like to see more videos like this, you can subscribe to this channel or follow us on Telegram as linked in the description. Okay, also feel free to sign up for trial lesson at the number that's also in the description below, and you can comment on what topic you would like to see covered next, and we'll try and bring it out to you as soon as possible. See you guys next time.